Topic 7. Waves. Part 3. Doppler effect. Doppler effect in sound waves. Doppler effect can occur in any type of waves, but here we just look at sound waves. When the police car is at rest and the siren is sounding, the sound is coming from a stationary source, which is the police car. The sound waves travel equally in all directions. The picture on the next page will illustrate this. This is the police car parked there, with its siren sounding, sending out these circular sound waves in all directions. And the wavelength of the sound waves, which is from one crest to the next, is the same everywhere in all directions. This picture here just shows the waves along one line only. The wavelength and the frequency of the sound waves from the police car is the same in all directions, as we saw on the previous page. Therefore, observers on any side of the police car will hear the exact same sound. Assuming that the speed of sound in air is 300 meters per second, and the wavelength of the siren is 0.4 meters. The frequency then can be calculated by using this formula here, speed divided by wavelength, giving 750 Hertz. If the police car moves towards the observer, the car catches up with part of the sound waves in front of it. The waves in the front becomes bunched up and have a shorter wavelength. In this case, we just assume that it's 0.3 meters. With the speed of sound being the same, the shorter the wavelength, the higher the frequency, and thus the higher the pitch. And the new frequency is now 300 divided by 0.3, giving 1000 Hertz. This picture here illustrates what we talked about on the previous page. This police car is moving towards its observer, and the waves in front of the car are more bunched up, as you can see. Here, similarly, the waves are more bunched up. After the car passes by the person, the waves behind the car are stretched out and have a longer wavelength. In this case, we just assume it's 0.5 meters. And therefore, there is an apparent change in frequency. The longer wavelength gives a lower frequency, which in turn gives a lower pitch. And the new frequency is now 300 divided by 0.5, giving you 600 Hertz. This picture here shows a situation where the police car had gone past this observer, and therefore the observer is behind the car, and the sound waves he is receiving have longer wavelength. This picture here illustrates similar things. Now we come to the formula for the Doppler effect. F prime stands for the apparent frequency, F is the actual frequency, VW stands for the speed of the waves, this one as well, and VS stands for the speed of the source, could be the ambulance, police car, whatever, plus and minus here. In other words, depending whether the source is moving towards the observer or away from the observer. Here we look at an example. An ambulance traveling at a speed of 30 meters per second sounds a siren of frequency 400 Hertz. The speed of sound in the air is 300 meters per second. What frequency would an observer hear when the ambulance approaches? Here is the answer with formula and working. I should have just written minus sign here to make the denominator smaller. Why smaller? Because we want the final answer to be greater. Why greater? Because we know that the ambulance is approaching the observer, and the observer is picking up an apparent frequency which is greater than the actual frequency. So the apparent frequency is 444 Hertz as compared to the actual frequency of 400 Hertz.